Let me start by saying right at the outset that unlike most of the speakers this morning, Michael didn't hire me at HAO. Nevertheless, he's going to play an important role in the story that I'm about to tell you. So, you're going to have to wait for it, but it's coming. The other thing I'd like to say is, here's the outline. It's, to get literary on you again, it's influenced by Dickens. It's exoplanets, past, present, and future. Where I'd like to end up is some statement about how might exoplanets fit into a reasonable program at NCAR that would study atmospheres of other planets for their own sweet sake. And as a sort of a footnote, to what extent should habitability concerns play into that sort of understanding? So that's where I hope to get to. But in the meantime, to begin with, the bulk of this talk is going to be a kind of an extended nostalgic romp through one of the most enjoyable parts of my career, which was the business leading up to finding transits on the first planetary transits, the first star that we knew had them. Then I'm going to jump ahead 15 or 20 years and give you a clue about what we think we know about exoplanets now. I think we're going to hear a lot more about that sort of thing from Natalie. So I'm not going to spend very much time on that. But I'll pick out a few items that I think are important and try to explain how we may learn more about them that have, to my mind, prospects in the future. And then finally, where exactly might those things lead, and what should we be thinking about as we make decisions about programs like that? So that's the plan. Okay. Exoplanets at NCAR. Let's actually start here. So there weren't any exoplanets that we knew about going around sun-like stars until 25 years ago. And the first of them was found by these guys. Didier Queloz and Michel Mayor, a couple of Swiss astronomers, and they located the first such known planet using the radial velocity method, which is illustrated here. The idea being that if you have a planet going around a star, then the gravity of the planet, or better yet, better way to put it is, to keep the center of mass of this system fixed, the planet has to go around in a little orbit while the star does. And so if you can measure the speed of the star relative to the Earth, and you see that it's moving in something that looks like it could be a Keplerian, then it probably is, and there's probably a planet there. So this is the radial velocity curve for 51 peg, radial velocity amplitude of sort of 50 meters per second, and a period, it turns out, of about 4 days. So that implied right there, and this is the first thing we learned about planets and other stars, it was that there are systems out there that are nothing like our solar system. We've got a Jupiter, because that's what it takes to make that big a velocity signal, that's within 10 stellar radii of its star. And so that's really cool. And that discovery was followed within a few months by several others because there were other people studying the same thing who had never imagined that they should look for a period that short. And so they went and interrogated their data again, and a couple more planets popped out. And meanwhile, the Swiss group had another one or two. And it went on like this for a couple of years. However, if you look at this picture, this is actually to scale, by the way. You look at this picture in a different way, then you realize that there's another opportunity here. So the apparent diameter of the star as seen from the planet is about 1/10 of a radian in the sky. And that means that the probability that an external observer placed in some random place on the sky will see transits is about 10% for a system like this. Just for comparison, to see Jupiter transit in front of the sun, the number of observers out there who get to see that is about a 1/10%, 1 in 1,000. The other thing is that since this thing had Jupiter mass, there's good reason to believe it had a Jupiter radius or more, and indeed it does. Actually, we don't know that about 51 Peg. But let's say it does, then it blocks 1% of the light from its star if it happens to pass in front, and that's a detectable signal. So at one fell swoop, we had gone from a completely inaccessible observational domain where we're trying to see Jupiters go around suns at 5 AU to a domain where you can actually hand it as a thesis problem to a graduate student. And you get a chance to see a transit every 4 days, and it's really visible. And you don't need all that many stars to have planets like this in order to see some. So it changed the landscape there and caused some of us to think about looking for hot Jupiters from the ground. So there were 2 bits of statistics that I would later present to Michael. One saying that by the time we were a year or 2 into this initial rush of planet discoveries, we were pretty sure that the fraction of stars that had hot Jupiters going around them was something on the order of 1%, 0.5%, something like that. Given what I just told you, the probability of seeing a transit, if you had a planet, was about 1/10. And the fraction of bright stars in the sky that are sun-like in some sense or other, you roughly estimate is about 1/3. Put that together and you believe that you have to look at sort of 3,000 stars for about 100 hours each in order to see a transiting hot Jupiter. Turns out it's not that easy because there are lots of other things in the sky that make signals that are similar. But this number is actually roughly right. And achieving those kinds of observational numbers from the ground is actually possible. And then easier because of point 2, which is you work out, now I want to look at a lot of stars continuously. What should my optical system look like in order to do that? Do I need a 4-meter telescope to do these observations? The answer is no. Turns out that what sets the number of stars you can squeeze onto your detector is the F number of your optical system, not its size. And so you want a short, stubby thing, but it can be as short as you want or as short as convenience allows. So you can build a small telescope with a big detector and have a reasonable chance of doing a survey like this. So next thing that happened was September of 1996. There was a meeting held here, actually down at the Foothills campus of NCAR, to push something called the Precise Photometry mission, which the final report ended up advocating for a telescope that looked remarkably like Kepler. It was a 1-meter Schmidt with a big detector. Its scientific goals were not principally or even, well, they were not principally planet detection. Astroseismology came first. Planet detection was in there. But it was aimed at sort of a lot of astrophysics that you could do with a system like that. And one of the technical questions was, what have we learned recently that would be helpful in doing this, and what experiments should still be done to convince ourselves that the things that you might want to do with a system like that are actually doable? The other interesting thing about this meeting is it was a small meeting, but look at the attendees. There are 11 people there. 7 of them, I think, if I counted right, are tied up closely with Kepler. This was sort of the crew that was going to move on and make Kepler happen. And in fact, a bunch of us had been working with Bill Barucki for a couple of years on previous unsuccessful attempts to propose to NASA for the same sort of thing that Kepler was. So anyway, this calculation, I presented this calculation that I showed you on the previous slide. And Ted Dunham, who had just moved from NASA Ames to Lowell Observatory, went home that night. He repeated the calculations. He got the same numbers that I did. He came back and said, why don't we do something about this? We've got some material, some stuff hanging around at Lowell that will help us build a prototype system of this sort. And so I said, great. And we set out to do it. Now, their stuff consisted of a World War II surplus aerial photography lens, Aeroectar, buyable for $150 out of the back pages of Sky and Telescope, a pretty nice telescope mount, and a pretty nice computer system to run the whole deal that they used for looking at occultations of stars by the moon. So we converged on the Lowell Observatory. There's Ted, in March of 1997. So this was a wonderful time. So, and I have vivid memories of it. It was cold and clear with a little bit of snow at Lowell. Mars was at opposition. So it was this 0 magnitude beacon overhead, visibly very, very red. And then off in the northern sky was Comet Hale-Bopp, which is arguably the best comet of the last 40 years. So it was really an okay time to be out under the skies doing real astronomy you thought was going to go somewhere. So we put this together, took some images. In the end, we didn't really take very many images with that system because the occultation people wanted their pieces back. But we did enough that we could get the analysis software going and convince ourselves, yeah, you can do what we wanted to do with a system that was this scale. So we moved the main pieces, namely the lens. Did I tell you it was radioactive? That lens was made with thorium glass, among others. And so we had kind of a high cosmic ray background rate. Not very radioactive. So at this point, though, we brought the pieces back to HAO, and at that point, I needed money. And so I went to Michael, and I told him, we need a CCD detector, we need a telescope mount, we need a computer to run it all up, $50,000, what do you say? Now, you have to understand Michael's position. So he is a division director in the National Center for Atmospheric Research. Said center is 90% tropospheric meteorologists. Okay, so solar physicists are already out in left field in this organization. I was talking about doing extrasolar planets, which wasn't even solar physics. It was barely related. And so he would have been perfectly within his rights to say, now, Tim, come on, why don't you do something that's at least kind of like our mission? But that's not what he said. He sat there and he thought for a minute or two, and then he slapped his desk and he said, I will support this. And he did. And he got pushback for it, probably more than I will ever know. But he stuck with it, and we stuck with it. And the result, pretty quickly, was this machine. So that's the Ionosphere lens, which is actually inside that big steel tube. We bought a Meade 12-inch telescope, put the telescope on the shelf, and used the mounting to hold this thing up. A little computer stuff and a little autoguider and spotting scope, and we were in business. We put the thing out on Tom Bauer's ranch, which is north of town. Tom had been the so-called wizard of optics at HAO for many years, but he had left a couple of years before. And our control room was in this building back here, which was in fact a chicken coop that Tom was going to rework into a clean room facility. But it was a good place, and accessible, and kind of a dark spot. So Steve Tomczyk and I, in 2 days, put together this little plywood fold-top observatory building known as the Dog House, and we started in. And after a year and a half, here's the same telescope that got moved to its subsequent location in the back parking lot of the Foothills lab of NCAR across the other side of town, because it was more convenient and because Tom thought we were scaring his cattle. Maybe we were. And this system worked pretty well, but it didn't work well enough. And its problem was big fuzzy images. It turns out that Ionosphere had fifth order spherical aberration that wouldn't quit. And so you get these images that look like mush balls. And so we concluded, well, let's build a Schmidt, because that will give us the image quality we need over the field that we need. And so the entire HAO instrumentation group went to it. Alice Lisinski, back there in the middle, was writing software for us. And Kim Strander was putting together mechanics, and everybody pitched in. And we ended up with this arrangement. And that was better. So that's what a full field image looked like with that camera. So this system was just getting into its commissioning phases in September of '99. And at that point, this guy showed up. Dave Charbonneau, whose name you've probably heard. He was a graduate student at Harvard working with Bob Noyes. He wanted to work on exoplanets. Nobody else at Harvard at the time was doing that. And Bob said, go out to Colorado and work with Tim Brown. And so he did. So he bought a car, drove out here. Anybody who knows HAO history knows that this echoes the original High Altitude Observatory, in which Walter O. Roberts and his brand new bride, they didn't actually buy their car. They would have bought a better one if they had. And they drove with the coronagraph parts in the back all the way from Boston out to almost Leadville, where they set up the High Altitude Observatory in 1940. So excuse me, some years later, Dave did something similar. And he showed up with all his brains and enthusiasm and skills, and he's a brainy, enthusiastic, skilled guy, let me tell you. And he also brought a piece of information, which was a star name, SAO 107623. It's just a catalog number in the SAO catalog. That star had been observed by Michel Mayor's group, and it was suspected of being an extrasolar planet. It wasn't, they weren't ready to commit to it at the time that Dave arrived, but it seemed likely. They thought they had a period. And so we decided, well, we got to look at something to commission the telescope. We might as well look at something that has a chance of being interesting. In subsequent months, we discovered that the SAO catalog was out and the Henry Draper catalog was in, and the equivalent name, it turns out, is HD 209458. I'm sure you'll agree that's simpler and easier than SAO 107623. So then, not too long after, here we are, 9/9/99, we got our first time series of what turned out to be a transit. And another one a week later. And then we were delayed in reducing the data because we had another project that we thought was higher priority. Didn't get actually a result out until November, by which time we had been caught up with by these guys, Henry, Marcy, and Butler, and ended up publishing our results in back-to-back papers in APJ letters in January. And so that was the first known transiting exoplanet. It was about the 10th one known. Chances of a transit were 1 in 10, so, you know, we were due. So a little bit after that, I got a phone call from Ron Gilliland. Now, Ron had worked here for some years with me. We did a lot of stuff together. And then he moved out to Space Telescope. And he was heavily involved with the STIS, the Space Telescope Imaging Spectrograph. And he said, well, you know, there's no instrument on Hubble that formally is able to deal with the light flux from a 6th magnitude star. We don't have a spectrometer, a photometer that'll count that fast. But if you use STIS, you can spread the spectrum out over many, many pixels, take short exposures, and you can actually cope with the light and turn it into a good signal. Now, I made a pretty good career by assuming that everything that Ron says to me is the gospel truth. And so I paid attention. And we got together with Dave, mostly, proposed for Hubble time, director's discretionary time, got it right away, and here's the resulting light curve, which I suspect is going to be showing up in undergraduate astronomy textbooks long after I'm gone. Anyway, that's a beautiful result, if I say so myself. And then a while later, as has already been described, we said, well, we've got, I mean, it was a spectrograph after all, so we can now make a time series of spectra. And when you do that, you find that indeed in the region around the sodium D lines, the planet is a little bit bigger than it is in the continuum nearby. And so that tells you that you are seeing light that's being blocked from going through the atmosphere of the star by the sodium atoms that are in the atmosphere. That blockage turns out to be less than theory would lead you to believe, and so we concluded that either the abundance of sodium in HD 209458 was significantly less than solar, or more likely there's a high cloud layer, so that the effective surface of the planet was higher than the kind of 1 bar pressure level that we would naively have supposed. And that, both of those make the lines weaker. So that's the first detection of an atmosphere in an extrasolar planet. And that's as far as I want to go with this story. It could rattle on indefinitely, but I think it's time instead to say, let's let's jump ahead 15 or 20 years and talk about what we've learned since then as an indication of where we might next be going. So to begin with, just one-sentence statements about exoplanets that we think are true. There are a lot of them on this slide. There are a lot more you could write down. I want to concentrate on 4 of them, one of which is, has already been mentioned. Thank you, Manfred, for pointing out that stars commonly have planets. In fact, as far as we can tell, for Neptune-sized planets and smaller, stars have planets the way cats have kittens. It just always happens. And the next question, if you're into exobiology, is, well, do planets have life the way that cats have kittens? And that's not nearly so clear. But we'll come back to that. Nevertheless, if you don't remember anything else from Kepler, remember this. Planets are really, really common going around stars that are anything like the sun. Then I want to skip down to these points. Hot giant planets, hot Jupiters, it turns out that they commonly have, so now they have strong longitudinal winds. They're equatorial jets. They go screaming around the planet to try to equalize the flux, or the heat load, between the strongly irradiated side on the sun and on a planet that's so close to its star that almost certainly it's tidally locked, so it always puts one face toward the star. It's doing its best to move the heat from one side to the other with an organized wind. How do we know that? What might we do to learn more than that in the future? So we'll come back to those questions. Similarly, hot giant planets commonly, apparently, do have high cloud or haze layers, because you can see the lines, the spectrum lines, not only of sodium, but of other absorbers, attenuated relative to what a clear air model would look like. And then finally, these two are explicitly about big planets and hot ones. Why is that? And why is that we don't know much about the atmospheres of small planets, like the Earth? Which is what we really want to know, right? Because we're like Trump. Everything is about us. Okay, so let's get into that. Winds. A powerful thing in studying a transiting planet is the phase curve. So you think about the planet going in front of the star, and that's certainly the main event. But as it continues around, let me scoot, you see more and more of the planet light up as you're able to see the illuminated hemisphere. And then eventually, it will go around and go behind the star, and you see the fully illuminated planet disappear behind the disk of the star. And that causes an eclipse. So if you can look at the variation of the total light from the system, you see a picture like this one. There's a deep transit. Well, this isn't very deep. This is 2.5%. Right? Remember, we're dealing with small numbers when we talk about the signals here. And there's a funny, slow variation as the day side of the planet comes more and more into view. And then just about the point where you see the planet at full phase, it disappears behind the star, and you lose some flux. If you blow up this upper part of the picture, you get a curve that looks like this. Especially if you do this in the infrared, then what you're measuring when you look at the phase variations in this part of the orbit is really variations in the temperature of the planet on the hemisphere, averaged over the hemisphere that's facing you. So look, the maximum here is not at the time when the planet disappears behind the star. It's later. And, the maximum is sooner. The secondary eclipse occurs later. What that says is the brightest part of the planet is not the substellar point. It's somewhere else. And you can do an inversion, and you get pictures like this, where the substellar point would be right here. And in fact, the region of greatest brightness is over here. And the reason for that, presumably, is because the hot material that's been blasted by the star only a few hundredths of an astronomical unit away is getting carried off to the east by a wind that has to be pretty close, well, half of sonic speed or something like that. It's a pretty fast jet. So that's how that's done. There's another way to learn about atmospheres of exoplanets, and that is kind of the traditional spectral sounding, remote sensing of an atmosphere, which you do if you're looking at it from the top, by picking a range of wavelengths. And here the author has chosen generalized ultraviolet, optical, and infrared. The atmosphere is less transparent in the ultraviolet than in the optical, than in the infrared. So in each wavelength, what you see is down to optical depth 1 in the atmosphere, and you see a roughly Planck black body radiating at whatever the temperature is at that height in the atmosphere. And so by looking at brightness as a function of wavelength, you can invert that and determine something about temperature as a function of depth. That's a potent technique. The problem is, if you do it when you're looking at a planet that is lost in the glare of its star, then the star is busy contributing noise, and all the signal comes from the planet. And even in the case of a hot Jupiter, the amount of light that gets radiated back to you by the planet is only, it's only this much. It's 1/10% or less, parts in 10 to the 4 typically. You look at Earth and the sun, and it's parts in 10 to the 10, 10 to the 9. So if you're going to do this successfully, you need to find a way to get rid of the light of the star. And that usually means imaging with a coronagraph that's good enough that can block out the starlight and let through the planetary light from a source that's only a fraction of an arc second, maybe an arc second away. And so this has been done in a few cases. There are a few planets that are far from their stars, 100 AU, 50 AU, something like that. They're massive, they're young, so they're still contracting and maybe even still accreting. And so they're hot. And you can see these self-luminous planets, 3 of them here, surrounding this crazy, totally saturated mess from the star itself. And so you need the wherewithal to get rid of all this so you can see that and then run those through your spectrograph. That's only been doable in a very few cases so far, but in some sense it might be the wave of the future. And then finally, there's the way that so far we have learned the most about atmospheres of exoplanets, and that's so-called transit spectroscopy. So in this case, you take advantage of the fact that when the planet passes between you and the star, you see this little annulus of light that's transmitted through the planetary atmosphere and on to you. And how big that annulus is depends on how opaque the light is, or how opaque the material is at the wavelength that you're choosing to look at. So if you look at 2 nearby wavelengths where the opacity is very different, then you see 2 different radii for the planet, and you can see a a signature in the spectrum. Now, how big is this signal? Well, it's pretty easy to convince yourself that this annulus is about a scale height deep. Because, I mean, what else could it be? I could make the direct argument, but, and a scale height, so if you say, so the light you have to work with is the scale height times 2 pi times the radius of the planet. What it has to compete with is pi times the square of the radius of the star. And so that ratio is something about your signal strength and tells you what signal to noise do you need. You can rewrite that ratio by writing out what it takes to make the scale height, and you get that the line depth is proportional to the temperature of the planet, the molecular weight of the atmosphere, because that goes into setting the scale height, the density of the planet, and the square of the radius of the star. So temperature divided by these three things multiplied together. So hot planets are, in fact, hot Jupiters are good because their temperatures are high. They're basically hydrogen atmosphere, so the molecular weight is small. The density of the planet is small, and the star is whatever it is. If you go through those numbers, the signal comes out to be about 10 to the minus 4. So that's the kind of signal, you need a signal to noise of 10,000 to be able to see this. For the Earth, it's a few times 10 to the minus 7. So now that's a different kettle of fish. On the other hand, if you take Earth and you put it at such a distance from 0.2 of a solar mass red dwarf, then it comes out to be something more reasonable, up to 10 to the minus 5. This, it turns out, is doable barely, and will be, well, and we'll come back to that. But this formula is important. Okay, so what have we learned that way so far? It's kind of surprising. There's actually a lot. There are detections of 15 or 16 different molecules and atoms in various extrasolar planets, most of them hot. And this is planet mass, so Jupiter is right here, Jupiter's there, Saturn's here. There are a few that are hot Neptunes, but they're all hot, most of them are big. And they are done by various clever adaptations. Mostly, all the blue symbols are transit spectroscopy. And imaging is mostly this ground-based emission, but also some with space telescope. Again, mostly on hot objects that are even, that are far from their stars because they're young. So that's kind of cool that we've gotten that far. So now we get into the future. What do we need to go further? Well, we need more signal to noise. Bigger telescopes, preferably with coronagraphs, preferably outside the atmosphere, although if you're willing to make your telescope big enough, you can make up for some of the defects of having air around. And there are, in the immediate future, there are two kinds of things you need to think about. One is JWST. It's going to be a powerful thing because it's got better spatial resolution than Hubble. It's got chronographs, and it's got spectroscopy that goes all the way across the wavelength range from reddish visible out to 30 microns in one instrument or another. The other thing that is coming up soon, 5 years, maybe that's soon, is the big ground-based telescopes, European, American, and maybe even Hawaiian, but nobody's banking on that at the moment. These have even better spatial resolution. They have huge light gathering power, and they can do spectroscopy within whatever the atmosphere will allow. And coronagraphs also in radial velocity capabilities, but we're not going to talk about that. And so these are the GMT, the Giant Magellan Telescope, the 30-meter telescope, the extremely large telescope. Europeans are so prosaic. Yes, overwhelmingly large telescope. I like that name so much better. So all these things are supposedly coming online in the next year for JWST and 5 to 10 years for the others. So, and then beyond that horizon, there are a couple of missions that are proposed. LUVOIR, which is a big multi-band, big might mean as much as 15 meters, telescope that does spectroscopy and coronography, and HABEX, which does the same, only if it needs it, it's got a star shield to block out the starlight and let you do even better coronography. So what do you make of this? So I think it's safe to say that with all that new equipment, the stuff we've been doing, namely looking at hot planets, hot big planets, that's only going to get better. We'll be able to look at spectra in much more detail and actually start to learn things about physical properties in those atmospheres that we can't touch today. But if what you're interested in is atmospheres on planets that would be habitable, meaning a rocky planet with a surface temperature that will allow liquid water to exist at the surface, then life is going to be tougher. And the reason is because you need those enormous signal-noise ratios, which you probably can't get unless the host star is bright by any reasonable standards. So Dave Charbonneau and his team, listed out here, have done a careful study of what they think is feasible with all of these, well, not at least JWST and the big ground-based telescopes that are coming up. And the answer is, they believe, barely within reach for a habitable planet in this sense will be planets that circle small stars, 2/10 of a solar radius and smaller, within 15 parsecs. So it turns out that with recent information from Gaia and TESS, we know what those stars are. There are about 400 of them. We know which ones have transiting planets. There are 6. One of them is TRAPPIST-1, which has lots of transiting planets. So total number of planets to look at is maybe a dozen. But this isn't much of a sample. And so I'm going to make the case that if you want to use NCAR's modeling resources and smarts and direct it toward exoplanets, there's a lot of science to do. There's a ton of it. It's just not this. Okay? So my prognostication is the future is very bright for studying exoplanets in general, and particularly those with hot hydrogen atmospheres. If you want to say anything definite about the presence or absence of life on exoplanets, or even about their habitability, that's going to be much, much harder. However, it's worth remembering that there's a consolation prize. There are I don't quite have all of my left Triton out of this. I've got 9 or 10 objects here in the solar system that have atmospheres that are thick enough that they do something interesting. And they're all a lot closer and easier to study than these exoplanets. So maybe we should be thinking about, NCAR, maybe you should be thinking about stuff like that. And I'll stop there. Thank you.